Hi everybody, Justin here from chemistrynotes.com, and we are starting a brand new section today. This is section 13. So my sections are kind of like chapters. So this is kind of like chapter 13. It's section 13, chemical equilibrium. Now in the last chapter we talked about kinetics, and that's how fast reactions occur, reaction rates, stuff like that. In this section we're going to talk about well, let me put it this way. Up until this point in chemistry, whenever we've been talking about chemical reactions or we write chemical equations and we balance the equation, we're always just kind of assuming that we're going from reactants to products, or that the reaction goes to completion, so to speak. It goes from reactants left to right to products. Now, often though, you can build up or accumulate products and you can get the reverse reaction to occur. And when that happens, you can get to a process called equilibrium. So this chapter doesn't focus on reaction rates whatsoever. It just focuses on reversible reactions and something called chemical equilibrium. So at the top of today's page 1, it says, chemical equilibrium, the state of a reaction in which the concentrations of reactants and products remain constant over time. First bullet point. In this section, in section 13, right, we will see how and why a chemical system comes to equilibrium, and we will discuss the characteristics of equilibrium. Now, we're also going to learn how to calculate the concentrations of reactants and products at equilibrium. So, chemical system is essentially just a chemical reaction, okay? Now, the second bullet point says something that I had said earlier at the beginning of this video. While most reactions, quote unquote, go to completion and proceed until the limiting reactant is consumed, some reactions stop far short of completion. So they're going to go from reactants to products, and then the products are going to, as they build up over time, they're going to go back to reactants, and we get this back forth situation. So let's talk about the first major topic of section 13, the equilibrium condition. The equilibrium condition is a dynamic condition. That means things are happening all the time. Things are always moving around all the time. It's a dynamic condition in which the forward and reverse reactions exactly offset each other. So, well, let me just mention something out loud here. It's kind of like if you have a helicopter and you're above the freeway and you're looking at cars on the freeway, right? At any given time, it looks like there's a certain number of cars on the freeway, right? But then there's on-ramps where cars are consistently coming onto the freeway, and there's off-ramps where cars are consistently coming off of the freeway. But over time, or at any given moment, there's a snapshot that looks the same. The aerial view from the helicopter always looks like the same amount of cars are on the freeway. That's an example of a dynamic equilibrium. All right, now, look at this graph here. We have a closed reaction vessel. H2O gas plus CO gas yields H2 gas plus CO2 gas. So at time 0, I have nothing but reactants. At time 0, before I've let the reaction go, I have nothing but reactants, H2O gas and CO gas. Over time, the concentration of H2O and CO decreases while we build up products, H2 and CO2. And so after a certain period of the early stages of a reaction, equilibrium is reached, in which both of those little lines on my graph flatline. That's the point where equilibrium has been reached, point X. All right. So a few bullet points about that graph above. It says at time equals 0, and really what I mean is shortly after time equals 0, reactants, brackets means concentration. So the concentration of reactants decreases as my concentration of products builds up. After a certain time, which I have marked X, equilibrium is reached. Okay? That doesn't mean the reaction stops. It just means the forward reaction is equal to the reverse reaction. We have a dynamic steady state or a dynamic equilibrium. Now, it says equilibrium is reached. Enough product concentration has been established, so now the forward reaction, reactants to products, equals my reverse reaction, which is products going to reactants. All right? Now, in the example above, look at the two flat lines. Look to the right of that dotted line on the graph. You'll see that the product concentrations are higher than the reactant concentrations. So it says, in this example above, equilibrium lies to the right. Quote unquote, lies to the right means we favor products. There are more products at equilibrium than there are reactants. All right? So still referring to that graph on the last page, it says at the top of our new page of notes here, at equilibrium, the concentration of products are greater in this example. All right? Now, I have a question I want to ask you guys, and that question is the following. And every time I ask a question like this, I always write the answer down so you have it in your notes. But the question is, what happens if we inject, fancy word for saying add more, what happens if we add more H2O gas molecules into the system? The reaction at equilibrium. Well, what is H2O? Is it a reactant or a product? We have to go up and look at our balanced equation, and I'm rewriting it for you now. H2O gas is a reactant. So if I'm going to add more reactant, okay, and I'm at equilibrium, my equilibrium doesn't like that, and it's going to have to make an adjustment and reach, it deals with the adjustment, and then it reaches a new equilibrium. So how are we going to put that into our notes? All right, so it says H2O gas. If you suddenly increase the concentration, brackets means concentration, if you suddenly increase concentration of H2O, well, there's more H2O around now, right? We have more of that reactant around, which we didn't just moments before the injection. So if I have more H2O reactant around, that means there's going to be more collisions between H2O and CO, H2O and carbon monoxide. Those are my reactants. So what happens to the forward reaction if I get more reactants colliding all of a sudden? The forward reaction speeds up relative to the reverse reaction. Now remember, we were at equilibrium moments ago, and now we add a reactant all of a sudden, H2O gas. Okay, so when we add that, the forward reaction speeds up relative to the reverse reaction. Now eventually, however, the reverse reaction will catch up. What do I mean by that? Well, when you have when you have more water molecules all of a sudden as a reactant and the forward reaction speeds up, you're building up products which will eventually catch up, and then the reverse reaction is going to again equal the forward reaction. However, we have a new equilibrium now, don't we, where more products are, the product concentration is even higher than it was before we injected the H2O gas. So it says here, the fresh new page of notes, bullet point at the top, it says, finally, a new equilibrium is reached, and that equilibrium has shifted to the right. We've got more products now because we injected a new reactant, which shifted things to the right. All right, double lines, star with a circle around it means I'm moving on to something else, and I'm going to do that in the next video. A general expression for chemical equilibrium. There is an expression we can write, and there is something called capital K, the equilibrium constant. We're going to get all into that right now in section 13, video number 2. So stick around for that.